Okay, thank you for coming to my talk. Yeah, so I will talk about systems of linear forms, and I'll explain what I mean by equidistribution and true complexity. So this work is a part of and uses a lot of tools from higher order Fourier analysis. And so higher order Fourier analysis is an extension of Fourier analysis that's initiated from the work of Gowers on his quantitative bounds for Semerity theorem on existence of arithmetic progressions of arbitrary long length in dense subsets of integers. It turns out that higher order Fourier analysis is very useful when you study problems that relate to the density of small linear structures in subsets of, let's say, an abelian group. So let's say that, so to make this precise, so let's say G is a finite abelian group. And I have a subset A of G. And so what is a linear structure? So two examples. So one is let's say I look at three-term arithmetic progressions in G. And such things can be represented by a nice analytic expression, which is the following. So just using the characteristic function of the set A. So I can pick x and y at random from the group. And then I look at 1a of x, x plus y, x plus 2y. Right, so this tells me what's the density of three-term arithmetic progressions in A. So another example could be triangles. In A, and this can be, again, represented by x, 1a of y, and 1a of x plus y. So these are two examples of small linear structures that people are interested in studying, and both of them seem to turn out to be controllable by actually just a Fourier analysis. So just the Fourier expansion of the characteristic function of A is sufficient to actually understand these densities. So what do I mean? So let's look at, for example, at triangles. So if I say f is just the characteristic function of A, then we know that we can write f its Fourier expansion alpha chi alpha of x. And I can just plug in the expansion in the expected value. So what do I get? Y G is equal to the sum of f hat of alpha, f hat beta, that gamma of expected value xy of chi alpha x, chi alpha y, and chi alpha x plus y. The sum is over the dual group. Oh, sorry. And because we're taking the expected value over x and y, the only terms that survive are when alpha, beta, and gamma are all the same. So this is simply sum over alpha. They're not the same, but so alpha and beta are equal to minus gamma. So this is really f hat of alpha times alpha squared. And this can be written as cubed plus squared. So what does this tell me? So this tells me that if A is a set such that all the non-zero Fourier coefficients are really small, then the number of triangles in actually my set A is going to be roughly equal to f hat 0 cubed, which is what you would expect in a random subset of the same density as A. Right. So basically, the maximum non-zero Fourier coefficient is a uniformity measure that captures the density, that controls the density of triangles. And similar things you can do for 3-term arithmetic progressions, but it turns out that there are many examples where you can't control such densities by the Fourier coefficients. Okay. And one example is k-term arithmetic progressions as soon as k is actually greater than or equal to 4. So we want to more generally talk about just systems of linear forms. So let's make a definition. So formally, what do I mean by a linear form? And actually, for the rest of the talk, I want to focus on only the case where G is the group Fp to the n. P is a fixed prime, and we think of n as a large integer. So whenever we talk about asymptotics, it's asymptotics according to n being large. So according to n. So we say that L in f to the L is so. We refer to every vector in f to the L, so f is going to be fp. Yeah, so for the rest of the talk, I may a lot of times drop the p. So we call this a linear form. And we will think of it as mapping vectors from fp to the n to the L to fp in the following form. So L, we think of it as a the n, where L of x is defined to be sum I going from 1 up to L of lambda I xi. So this is the ith vector. Okay. So again, so let's just look at the example. So under this definition, a 3AP is simply a collection of 3 linear forms, L1 being 1, 0, L2 being 1, 1, and L3 is 1, 2. Okay. So this is just the first vector, sum of the first 2 vectors, the first vector plus twice the second vector. And the triangle can be represented as just 1, 0, 0, 1, and 1, 1. Right. So a very useful definition for so it was defined by Green and Tao. So there was a notion of complexity defined for a collection of linear forms. So by Green and Tao, this is Cauchy-Schwarz complexity. So this is a notion of complexity that then you can define a uniformity norm that using this complexity, you can actually control the density of such linear forms. So what is so I will first define the notion. So let's say L1 up to Lm, the L are linear forms. So the Cauchy-Schwarz complexity of L1 up to Lm is the smallest d such that you can do the following. So for every I, we can partition all the linear forms Lj such that j is not equal to I into d plus 1 groups such that Li is not in the span of each group. So Li is not in linear span So this is kind of a strange notion, but so the motivation for this was the fact that for every I in M, we can partition all the linear forms except Li into d plus 1 groups such that Li is not in the linear span of the vectors in each group. And the motivation for this is that you can actually use repeated Cauchy-Schwarz to prove something about these linear forms. So this leads us to, so we will need so this is still fp to the L. So f will be fp for the rest of the talk. So Gowers, as a part of his work on semi-reduced theorem, he defined a collection of a sequence of uniformity norms that are now known as Gowers norms. And these exactly. So yeah, so that's a good example. So for KAP, CS complexity is k minus 2, and you can see this by for every linear form you have to partition the rest into single groups, and otherwise you will have the linear form in the span. So this is useful when we think of the sequence of norms that are known as Gowers norms. And so because we will talk about Gowers norms a lot, so I will actually make precise the definition. So let's say that I have a but so this is not the dimension. So you have to, so if I have x plus y, x plus 2y, let's say, so this is a 3-term arithmetic progression. So if I pick this as my Li, then you have to put these into 2 different groups, because otherwise you have x in the span. If you put these 2 in the same group, then you have x in this.
So for k, put k linear forms, it is most k minus 2.
As long as they're pairwise linearly independent. So if they're not pairwise linearly independent, then in fact it's infinity, right? Because so it's yeah. So let's say that I have a complex valued function f over f to the n, and let's say that d greater than or equal to 0 is an integer. So the UD norm of, so this is the dth order Gowers norm of f, is defined by the following expression. So we pick x, y1 up to yd. So these are going to be vectors from f to the n, and we look at the following product over all S subsets of D of size of S of f of x plus summation I in S yi, and then the whole thing to the power 1 over 2 to the d. So, okay, so let's stop here for a moment and understand what this is. So this is going to be the complex conjugation. So this means that we conjugate the size of S times. So we're picking x and y1 and up to yd. You can think of these as directions. And you look at the whole d-dimensional cube with the center x, and you evaluate f at each of the corners. You look at the product. So, and then you normalize it by the power 1 over 2 to the d. Okay. So let's look at an example. So the u1 norm becomes simply x and y of f of x times f of over 2. This is really just the average of f. So the absolute value, the norm of f, average of f. So this is not a norm. So this is just a semi-norm. But it turns out that for all d that's at least 2, then the Gowers norm becomes a norm. So d greater than or equal to 2, ud is a norm. So this turns out to be actually the right uniformity norm for in many different contexts, one of which is actually when we study the density of linear forms in functions. Feel free to stop me whenever I'm going too fast over this. Okay. And the relation to the density of linear forms is exactly described by the Cauchy-Schwarz complexity. In particular, there's a theorem of Green and Tao that shows that if L1, Lm be linear forms of Cauchy-Schwarz complexity D, then the following thing holds. So if I give you any set of functions, f1, fm are bounded value complex valued functions over f to the n, then the following is true, that so if I pick a vector x from f to the n to the l, and I apply my function fi to the linear form li, this is bounded by the minimum ud plus 1 I. So in particular, if I just pick all of my functions to be the same function, that's just the difference of the characteristic function of a set minus its density, then what this tells me is that, okay, so let me actually write that down. It's the complexity.
No.
Oh, so this is going to be C such that. Or otherwise, you have to normalize this by the L infinity norm of the fx. So if I let f be, again, so the characteristic function of some set A, and I look at G, which is f minus some constant alpha, then we can use the Green-Tao theorem to do the following. So I claim that the expected value of f of L1 of x for x in L minus alpha to the m is bounded by m times the minimum. Oh, m times just the p plus 1, where this is the CS complexity. So why is this true? You can just really apply the chain rule. So you can look at this difference and write f as g plus alpha, and then just expand it out with terms that each of them has at least one appearance of g. But this is simply g, right? So basically, if I have a set A where the Gowers norm of my characteristic function minus a constant is small, then I know that my set actually behaves random according to the collection of linear forms. Okay. However, it turns out it was observed by Gowers and Wolf that this is not efficient. So this is not the optimum uniform. So this might be actually wasteful. So there are cases that this is too strong of a uniformity norm to require for this to happen. In particular, we know that Gowers norms satisfy the following. So we know that for any function, u1 so the Gowers norms are increasing. And if you require a larger Gowers norm to be small, so you're actually requiring a stronger uniformity condition. And Wolf observed that there exists linear forms. There's many examples of linear forms such that the density of the collection of linear forms can be controlled by some US plus 1 norm where S plus 1, S is strictly less than the Cauchy-Schwarz complexity. And let me give you an example of So in particular, so you can pick the linear forms x, x plus y, x plus z. And this will have a Cauchy-Schwarz complexity two, but their density, they showed that can be controlled by U2 norm. U2 norm. And the Green-Tau theorem uses U3 norm to control such a thing. And so they went on, motivated by this, they defined the true complexity of a collection of linear forms. And this is just defined to be the smallest Gowers norm that you need. So this is smallest d for L1 to Lm such that for all f to d, so the following holds, that for every epsilon there exists a delta such that for all f f minus alpha being smaller than implies that f of L1 of x up to f of Lm of x minus alpha to the m is less than or equal to epsilon. Yes. So you won't have exact bound by the UD norm, but you can actually require it to be small enough would imply that you have approximation with. So the delta will depend on p. Yes.
No, I mean D. L1 to Lm. I mean they're just linear.
Oh, so these are still in FP.
I mean the example you gave is not.
Yeah. So you have to. I mean, so this. I think of it over FP to the n. So. I mean, so there can be a lot of examples where it's different over F2 versus F3, right? So. And they also conjectured a characterization of the true complexity. So there's a nice linear algebraic characterization of the true complexity, and this is their conjecture. So this was defined by Gowers and Wolf. The true complexity of a system of linear forms is equal to smallest d such that the d plus first tensor powers of your linear forms are linearly independent. So I'll just define what I mean by the tensor power are linearly independent. Okay, so the conjecture that the true complexity is the smallest d such that the d plus first tensor powers are linearly independent, and if L is lambda 1 up to lambda L in f to the L, so the dth tensor power of it, we define it to be the product of lambda I j going from 1 up to d for all I1 up to ID that is in L. So you basically pick any collection of L and D entries from lambda 1 up to lambda L, and you pick the product. So this will have L to the D dimension. Okay. And they in fact proved something about this. So they proved that this for the case when the size of the field is really large. So the theorem Gowers and Wolf is that so conjecture holds when is greater than or equal, is strictly greater than the Cauchy-Schwarz complexity. However, this is a very strong assumption to make. So we are requiring the Cauchy-Schwarz complexity to be constant, and then we're requiring the p to be larger than the Cauchy-Schwarz complexity.
Can you give us some intuition to the conjecture?
So the conjecture is so it comes from the way that these will be related to higher order Fourier expansion. So you will actually pick any function that you're studying, and you want to decompose it and write it as a function of some degree d polynomials, let's say. And kind of, at least the way we prove it is the fact that if these are linearly dependent, then you actually can have a homogeneous degree d plus 1 polynomial will vanish. There is a linear combination of it. So these can be thought of as coefficients of a degree d plus 1 homogeneous polynomial applied to the linear forms. So I'm not sure if I can. So if Q is a degree d polynomial, then so let's say that sum of ai li to the d plus 1 was 0. Then this implies that actually for any homogeneous degree d plus 1 polynomial, sum of ai q of li of x is the constant 0 function. And in particular, so you can do other things. So we will show that if you don't have cancellation, and if polynomial was what we call a uniform polynomial, then not only you don't get a cancellation, you will get something that's unbiased. So we will see how. So we'll go through. Yes. Yeah.
So maybe
Thanks. And this is for every.
maybe it's obvious, but probably good to say that like the Gowers norm of degree b something before.
Yes. So we will get to that as well. Yes, so this will be between 0 and 1. Yes, so normally we would think of it as the average, yes. Sorry? So it won't be like bounding it directly. So it will say that if the Gowers norm is small, then so it won't do it directly the way it's defined, but that's one of the things that we prove. So let's see what we prove. So we actually prove the conjecture. So this is a theorem now. So with Hatami, myself, and Lovett, we prove the conjecture. Is true. And we actually, moreover, prove something stronger. So we prove the following theorem. We say that assume that d greater than or equal to 0 is such that L1 to the d plus 1, Lm to the d plus 1 are linearly independent. And so let's say that I'm given a collection of functions. Oh, so again, so for every epsilon, there exists a delta such that the following holds. For every epsilon, there is a delta that depends, can depend on m, d, and size of the field, and epsilon, such that for all Fm, d minimum of the u d plus 1 being less than or equal to delta implies that the expected value of your functions applied to the collection of linear forms is small. So f1 of L1 of x for x in f to the n to the L. So, and I from. So it says that if we have this linear dependence, then in fact, even one of these functions having small Gowers norm is sufficient to actually bound this collection of linear. And this again implies by the same argument, it will imply this theorem for the true complexity. Moreover, it will actually imply a stronger thing. So you don't need alpha to be a constant. You can plug in any function that you want. So you can actually plug in for every fi, you can have a gi such that fi minus gi is small. Then it would mean that this will be close to the same average with gi's. And so the proof of this relies on an equidistribution theorem that was also in the title. So uses a new equidistribution result for theorem for uniform polynomials. So before I can actually formally state it, I have to make a few definitions. But roughly speaking, what it says is that if I have a collection of polynomials that are roughly random, so we call them a random collection, a pseudo-random collection of polynomials, and I look at the following matrix. So each entry will be one of my polynomials applied to one of the linear forms. P C of L1 of x. X. Then what we show is that actually, this matrix will be almost uniform over its image. So this is image if P1 and up to PC are uniform. And we will see in a second what we mean by uniform collection of polynomials. So note that we couldn't require the whole matrix to be exactly uniform, because so if I just look at one row, then we could actually define this, and this is how it is done in the literature. So if I have a collection of polynomials, we call it uniform if every linear combination of them is unbiased, and that would immediately imply that if I apply them to the same input, random input, then this whole vector, its joint distribution of its entries, will be close to uniform over any choice from F to the C. However, because I'm applying same polynomial over a collection of linear forms, I can do things like taking derivatives, right? And polynomials have this property where if you take enough derivatives, they will vanish. So you could possibly make this one of the rows to be completely dependent on the rest of the rows. But what this theorem says is that up to those linear dependencies, everything else is almost uniform.
You mean you can take derivatives by putting the right linear form?
Exactly, yeah. So if I put P1 of x, x plus y. So just now. So I'll just write the definition for uniform. So if P is a polynomial Fp, then we call it epsilon. P is epsilon uniform if the Gowers norm of E of P, which I will just explain what this is, u to the degree of P is smaller than epsilon, where E of x is defined to be e to the, let's say, EP of x, e to the 2 pi I over P times x. So this is the pth root of unity, a pth root of unity to the power x. We call a polynomial to be uniform if its Gowers norm in the right order is small. But we also want to define a uniformity for a collection of polynomials. So we say that PC are, as a collection, if for every in Fp is small, where d is equal to the maximum of degree of lambda I pi. So if all the linear combinations have small Gowers norm, then we call the collection to be epsilon uniform. Okay. So let's think about the Gowers norm. So if P is a degree D polynomial, then we know by the fact that the D plus first derivative of P will be 0. So we know that P d plus 1 will be identically 1. Why? Because so the d plus first Gowers norm can be thought of taking the d plus first additive derivative in the exponent of p. Okay.
If is the maximum degree of lambda IPI, what if you would take the degree of sigma lambda?
So yeah, so we don't want to do that because then you could actually, this would mean that you can have cancellations and so on. So this is a stronger thing to require. Right? So the degree of the summation is smaller than. And this can be.
Can you say it again? What you said about?
Yeah. So let me actually make a formal definition that will make this clear. There's two definitions. So one is the multiplicative derivative of a polynomial. So of a function. So let's say that to C, then the derivative of multiplicative derivative of f is defined as f of x plus h times f of x. And the additive derivative of an f-valued function, or in fact any additive group. So d h of p of x is p of x plus h minus p of x. Okay, so these are things that we will keep using. And why they are useful is the following. This p is that the Gowers norm is really just the expected value of delta y1, delta y2, delta yd of f of x to the 1 over 2 to the d. And in fact, if f was itself an exponent of a polynomial, then you could rewrite this as, so if f was e of some p, then you can actually write this as expected value of e of dy1, dyd of p of x. Okay, so now just thinking of this would imply what I just said here, is that so if I take ud plus 1 norm of e of p, then I'm taking really the d plus first derivative of a degree d polynomial. This always will vanish. So you will just have a constant 1 average. However, it turns out that there are more functions where their ud plus 1 norm is equal to 1. So this was so degree. So this is a lemma, let's say, degree d polynomials are not the only functions for which and motivated by this, we define what are called the non-classical polynomials, which will be exactly the functions where this will happen for them. And in fact, that's the existence of these non-classical polynomials is what makes this work. So that's basically the technical barrier here. So because everything is very nice when we work with polynomials, but non-classical polynomials turn out to be a little bit more difficult to work with. So definition. So we call a function f that maps f to the n to the torus, where the torus is a non-classical degree d polynomial if dy1 of x is identically 0 for all y. And this is what it means that. Okay, so we just define any function of this form to be a degree d polynomial if this happens. And the degree of a function will be the smallest d such that this works. So this.
And for this degree, right, so polynomials that take only binary values, for example, then it's even only, so you don't have any non-classical.
So the polynomials that are, so yeah, so if I replace this by fp, then those will be the only ones. Yes. So the problem here is that we are working with functions that are devalued, and if they even take values that are exactly on the unit circle, then they can be written as exponent of something that's not necessarily fp valued, right? So that is the thing, and we know that for any function, so this is a simple claim that d, then the ud plus 1 norm of f is 1 if and only if f is e of some p, where p is a degree less than or equal to d, non-classical. And from now on, so when I drop the subscript e, I mean e of x is e to the 2 pi I x. So we don't have division matrix. So e is a, sorry? F is any function. Any function that takes values in the units. Yeah, that is any function. But that's r over z value.
Yeah, no.
All right.
It's not polynomial, but it's not a real polynomial.
Yeah, so it's a non-classical polynomial. So you can define polynomials in two ways. So one is whether they are a linear combination of monomials, and one is whether their d plus first derivative is 0. And when you're thinking of functions that are fp valued, these two definitions coincide. So one of them is like a local definition, which is, so for every directions, d plus 1 directions, the derivative is 0. And the other one is a global, so your function is written as a linear combination of monomials. So when we change t, then it turns out that these two things don't coincide. So you just monomials don't suffice to describe them.
Here the real polynomials correspond to functions that map to integers divided by t, like I over t.
Yeah, so the classical polynomials, you can think of them as a polynomial, fp valued polynomial divided by p mod 1. Right? So even though they sound strange, we actually have, there exists a nice characterization by them thanks to Tao and Ziegler. So there's a theorem by Tao and Ziegler in their paper on the inverse theorem for Gowers norms over finite fields. They show the following characterization. So we say that a function p f to the n to t is a degree d non-classical polynomial if p of x can be written of the following form. So it's a shift of the following. So we have d1 up to dn, which are less than or equal to p minus 1. We have a k that's greater than or equal to 0. And we require that d1 plus up to dn plus k times p minus 1 is less than or equal to the degree. So it's somewhat technical. K So this is kind of similar to what happens over FP. Now we have more complicated monomials, multinomials. So alpha is going to be a shift, what we call it the shift. So alpha is a constant. And so these coefficients will take values so these are integer valued coefficients that take values from 0 up to p minus 1. So this absolute value denotes just the map from fp to 0 up to p minus 1, the standard map from. So if I plug in 2, it just gives me the integer 2, and so on. Yes, and then we have this k is called the depth of a monomial, and everything is done modulo 1. Okay, so this is.
So again, what is the absolute value of z?
So the absolute value is a map from fp to 0. So that's what makes them behave a little bit strange. So for example, if I want to, so let's look at an example of a non-classical polynomial.
So it's any map that they choose.
Oh no, it's just the standard. So map 0 to 0. Yeah. So just yeah.
Just the
Yeah. So the standard map. Yeah. And this is in fact unique. So the coefficients are unique. So the same way as that. So these things are orthogonal to each other. So they're not that easy to work with when you're applying a polynomial to a linear form because of exactly this absolute value. Because you're doing arithmetic over two different fields. So if I look at x1 plus x2, then you're taking a mod p, taking the power, then doing things over mod p to the k.
And the content of the Tau-Ziegler theorem is that a thing that's defined as non-classical in your definition above can't be written like that.
Yes, every such thing. Yeah.
So you give some examples.
Yes. I can't say much about why it is true, but so some example of a, let's say p is equal to 3, then x1 squared over 9 mod 1. So this is a non-classical polynomial of degree. So its degree is 2 plus, so this is 3 squared So its depth is always just 1 less than the power of a p that's in here. So it's degree 2 plus 3 minus 1 times 1. So it's really a degree 4 polynomial. Okay. Or even over f2, so I can have things like x1 over 8 mod 1 is a cubic. And there is some nice properties of this thing. So if I have a degree d, okay, so the depth of a non-classical polynomial will be the largest k such that there is a non-zero coefficient. There is a term with a non-zero coefficient. Okay. And in particular, if the depth, so
Can you explain why just to grasp it, why is non-classical?
I don't I don't know the proof or how it is.
No, just one example to see that it's
Yeah, so taking derivatives is complicated. That's what I refer to. So it's not even easy to represent what x1 plus x2 squared over 9 expands to, because you want to actually write it as again of the same form. So they don't behave as nicely as the polynomial. So you can't just expand simply something like x1 plus x2 squared over 4 if you're, so then this is not simple to actually represent. In fact, most of the techniques that are used are somehow taking enough derivatives that makes things classical that you can actually get around with thinking about these things. And if the depth of P is K, then P takes values in 1 over P to the K plus 1 C over C. It's a shift, but so for the rest of the talk, we will think of the shifts, all of the shifts of the polynomials being 0. Okay, so we think of the 0 shifted polynomials, and everything else will. I mean, you can adjust everything to actually include alphas that are non-zero. And we also know that for any polynomial p, the degree of p times p is less than or equal to maximum of 0 and degree of p. So when you're multiplying by p, you either make your polynomial 0, or your polynomial was 0, or you're decreasing the depth. And so those are the things. And as Avishai pointed out, you can think of classical polynomials are in 1-to-1 correspondence with depth 0. Depth 0 non-classical polynomials. So we want to show that for any collection of polynomials, that now we are thinking of these as non-classical polynomials, that are epsilon uniform of degrees d1 up to dc and depths k1 up to kc, then for any possible linear combination, so these are z-valued, integer-valued linear combination of them. So I define the p sub lambda to be the linear combination of your polynomials applied to a collection of linear forms. Then we show that one of the two things holds. So you either have complete cancellations, so this linear combination is 0 for any choice of x, or in fact, the Gowers norm of your linear combination applied to the linear forms is at most epsilon, the uniformity parameter. So this theorem was proved for the case where the size of the field is large by Hatami and Lovett. And it was proved for the case where the linear forms are affine collection of linear forms by us with Bhattacharya, Fisher, Hatami, and Lovett. So we proved this without any assumption on the linear forms. However, we make an extra assumption that the polynomials are homogeneous. So this is usually a very harmless thing to assume when we're working with classical polynomials. However, when we're talking about non-classical polynomials, this is not only, so we don't know whether it's harmless or not. We don't even know what it means for a non-classical polynomial to be homogeneous. So we have to actually define what I mean by homogeneous. So recall that a degree D homogeneous classical polynomial. So it has this nice property that P of C times X is always C to the degree of P of X. Okay? And this is what we really need from what we mean by homogeneous non-classical polynomials. And this is not easy to satisfy. Because if you look at the way the non-classical polynomials are defined, if I even look at one monomial, it's not clear that it does satisfy that. So if you just plug in Cx, it will not, in fact, satisfy the.
Are there, in fact, any sort of
homogeneous
algebraic properties in non-classical polynomials?
So we show some things that I'll talk about. So for example, we show that so the theorem of us that so for example, homogeneous polynomials at least span the. Oh, so let me actually first define what homogeneous non-classical means. So T is homogeneous if for all C P of Cx is equal to C P of X. So C is for all C and no, so that's not C. So there's a okay. So for all C in, let's say, in FP, P, there exists some sigma C such that this is equal to sigma C times P of X. So we don't get C to the degree. We just require some constant. And you only need to have this for a generator of a multiplicative group of FP, and then that will you can repeatedly apply to get what you wanted. And the theorem that we prove is that homogeneous polynomials linearly span all polynomials. And so in fact, homogeneous polynomials of degree less than or equal to D span polynomials of degree less than or equal to D. And another theorem that we show is that for all d and k, so if I fix eta a generator of f star, there exists a unique sigma dk mod p to the k plus 1, such that every degree d polynomial of depth k will satisfy p of eta x is sigma p of x, such that every homogeneous dk polynomial p, p of eta x is equal to sigma dk p of x. So this is very important. So we will make use of this repeatedly. So it says that the only thing that, so whenever I have p of some constant times x, the only thing that I need to rewrite it as in this form is the degree and the depth. It doesn't depend on the structure of the polynomial itself. Okay, so now so I'll try to prove this theorem and then give a high-level proof of the Gowers Wolf conjecture. So for the rest of it. So recall, so let's say, so what do we have? So we have p lambda, which is a linear combination of the non-classical polynomials applied to the linear form. No. So the way it is proved is inductively. So you induct on the depth and the degree. So the depth 0 is just, it's the simple. So we prove it for univariate polynomials. And you use the following property of the non-classical polynomials, that p of cx minus c to the d p of x. So this is not hard to prove. Lemma. That the degree of such a thing is always strictly less than degree of p. So they don't have a very nice structure, but at least they have this. So, and you can use this to kind of do an inductive argument. And so this is for any non-classical degree d polynomial. So degree of p. Okay. So yeah, you can't take c out, but you have that at least the degree of it as.
Because this is on FP and this is on the top.
Yeah, so as an integer. So here you think of it as fp, here you think of it. And this is, so the way, this is the derivative technique. So the way, for example, such a thing is proved is by taking d derivatives, degree of p derivatives of this. So I take dy1 up to.
It doesn't make a lot of sense because modulo 1 is. Okay, because p is mixed. Okay.
So this has a high depth, right? So cx. So you can show that. So you can show that if I take enough derivatives, so the right amount of derivatives of p, this polynomial becomes classical. Not only it becomes a classical, it becomes a homogeneous classical. Of the same degree. But what does that mean? That means that this is really equal to c to the, so c to the degree of p but this identity tells me that if I take d derivatives of this polynomial, it vanishes. So it means that the degree of it must be less than p, degree of p. Yeah, so this. But I don't want to, because we don't have so much time left. So how do we prove this? So the trick is to apply many transformations and simplifications to the collection of linear forms that you're dealing with, so that it's nice enough that a whole bunch of Cauchy-Schwarz inequalities suffices. So as it's usual in this field. So everything is by Cauchy-Schwarz inequality and taking derivatives. But what do I mean by a nice form? So our goal is the following, that for all ij, okay. Another thing is that for a linear form L lambda L, we define its absolute value to be just the sum of lambda i's. So it's kind of the weight of your linear form. So our goal is to rewrite that summation in a form that degree of lambda ij p I is always greater than or equal to the absolute value of Lj. So this is, you will see why. And another thing that we want is that the first non-zero entry in each Li is actually 1. So our system of, so we want to reduce to this case where we can make these two assumptions. And this means that, so our linear forms are not affine, but at least their first entry, whatever happens, the first non-zero entry is 1. And this will be good enough for some sort of a derivative technique to hold. So the first claim is that I can always at least assume this without loss of generality. So that actually so in my linear combination, the linear forms have lower weight than the polynomial that they're being applied to. And this is really because of the derivative property. So assume, so I want to say that without loss of generality, we can assume that Lj is less than or equal to lambda ij. So the way we prove it is the following. So we show that if I have any polynomial p, and then any non-classical polynomial p applied to a linear form, can always be written in the following form: am p. So where m is a linear form. So how do we prove this? This is simple. So you assume that L had a heavier weight than p. So we know that the d plus first derivative of p is 0. Right? So in particular, we prove this. So we say that if it's greater than the degree of p, then we know that dy1 dyl of p at any input x is going to be 0, identically 0. But now you can plug in y1 and up to yl carefully. So choose y1, yl to be x1 up to xl, where xi is repeated lambda I times. So where lambda I is the ith entry of your linear form. So then if you expand this out, there is the maximum weight p of L of x is going to be exactly this, and you can write it as a linear combination of lower weight ones, and then you can do induction on the weight of the linear forms. Okay? So that's the first claim. So the second claim is that I can actually write P of L of x always as a linear combination of some AM and C of P of Cm of x, C times M of x, where C is in Fp and M is in F to the L. Size of M is less than or equal to degree of P, and its first entry is 1. So again, so we prove this. So we prove this by induction on in fact the support of L. So what do we do? So we look at the first entry of L. We pick. So we can assume that the first non-zero entry is lambda 1, let's say. So we pick C to be lambda 1 inverse. And we know that P of L of x is equal to P of lambda 1 inverse times some capital M of x. And so now this M is some, it might have a heavy weight, but at least we know that its first non-zero entry is 1. And now you apply the previous claim that we proved somewhere. Yeah. Okay. So and we apply it to the polynomial p prime. That's p applied to lambda 1 minus 1. And then you rewrite it as a lower weight ones. But the point is that because the first entry is 1, you either have zeroed out that entry, or you have a lower, which is a lower support, or the terms that you got out of the claim actually satisfy the conditions that you wanted. So you can work this out, and then finally. So now is the time that we actually use the homogeneity. So if the polynomials that I have are homogeneous, so I can look at my linear combination, apply this claim to them, and what I get is some pi times some constant times a linear form. But because they're homogeneous, I can just take the constants out by the definition of homogeneity. And I can finally write, so without loss of generality, 1 and 2 whole. Okay? And so this is not, so we repeatedly apply this claim and homogeneity. Okay, so finally, the linear combination is a nice form that we can take derivatives. So how do we take the derivatives? So there's another important fact that all the three claims that we proved contain is that they never depended on the polynomials. So they only depend. So the first two claims, so this only depends on the degree, because we only used this fact. So the coefficients we get will not depend on the polynomial itself. And here as well, and here when we apply homogeneity by this theorem, it only depends on degree and the depth. It doesn't depend on the specific polynomials themselves. So by this argument, so we know that after we made this assumption, let's say we name it p lambda prime, either all the coefficients, so now we have that this is equal to lambda prime ij pi of Lj of x. So I claim that if all of these lambda prime ij pi are 0, so the whole thing is 0. I claim that otherwise, then the second part of our theorem holds. So otherwise, we actually have no cancellation, and we will get to something that's unbiased. So we prove that if there exists ij such that lambda prime ij pi is not 0, then p lambda is not 0, and expected value of E of p lambda is smaller than epsilon. So what this would also mean is that if you had full cancellation, then your linear combination applied to the linear forms is in such a way that you can replace pi with any degree d depth k homogeneous polynomial, and you will still have cancellations, full cancellations, and otherwise you don't have it. Okay, so how do we take the derivatives? So we define a way of taking derivatives of a polynomial on L vectors. So where y will be a vector in f to the n, this will be a vector in f to the L. So this will be p of x1 plus alpha 1y xl plus alpha ly minus p of xl. Okay. So we could actually pick L different vectors, y1 up to yl. So this is a more restricted way of taking the additive derivative. So I'm actually taking, for each of xi's, I'm really taking a product of, so a multiple of y as my direction. But this is very useful when applied to a polynomial over a linear form. So in particular, if I take d alpha y of p of L of x is really equal to p of L of x plus so this is nice. So x is really a collection of vectors, right? So x1 up to xl. So when you apply it, then you really get L of x plus these directions, and this becomes exactly the inner product of alpha L and y. But this is nice. It means that if I pick alpha such that alpha is orthogonal to L, this derivative is 0. So this would kill any polynomial that's applied to a linear form that's orthogonal to alpha. Okay, so we pick M star in not L Lj with okay, so I want to look at this summation and look at the non-zero terms, and I will pick the Lj that appears with the first, so the smallest first, it's the index of the first non-zero entry. So pick Lj with smallest index of its first non-zero entry. And then we pick I such that degree of lambda ij, lambda prime ij, pi is maximized. Okay, so Lj is picked among the linear forms where there is a non-zero. lambda ij pj. So now I define the derivative directions. So I define alpha 1 to be E1, alpha. So let's say that Lj is also equal to WL. And without loss of generality, let's assume that the first entry is just a W1. So alpha t be all vectors of the form 1, where this is ith entry and w is less than or equal to wi minus 1. And further, we define alpha t plus 1 up to alpha d to be, again, E1. So why am I doing this? So the point is that this will kill any vector. So if I take derivatives from alpha 1 up to alpha d, so this will kill any polynomial that had lower degree. It will also kill any polynomial that's applied to a linear form where the first entry is 0 because of just alpha 1. And it will also kill any, so here I also want it of maximum weight. So the only thing that could survive are Lj itself or linear forms that the first entry is 1. But because Lj was of maximum weight among them, such a thing must have an entry which is lower weight than some entry of Lj. So let's look at, so this is the claim. If either Lj prime's first entry is 0 or degree of lambda prime I prime j prime pi is less than d, or Lj prime is equal, Lj prime 1 is equal to 1, and j is not equal to j. So this will kill all such things because, so the first two are easy to see because, so this is because we take a derivative at E1, and E1 is orthogonal to this. This is because we take d derivatives. And this is because if you have j prime is not equal to j, so there must be some entries that Lj is different than Lj prime. But because they are equal in the first entry and Lj is of maximum weight, Lj prime must have a lower weight entry. And we are taking a derivative at that weight, minus w and exactly that index. And Lj prime 1 is equal to 1. So minus w times that entry will be 0. So these are going to be orthogonal. There is going to be some direction that's orthogonal to it. So after we take this derivative, so as a result of this, if I take so if I actually take this derivative of the whole thing, so I can use the linearity of the derivative. I apply it to every term in the summation. So So what survives is only ij such that degree of lambda ij prime pi is equal to d. This is only I. So we know that no other j will survive. So this is going to be lambda ij prime pi, the whole thing applied to Lj of x. Oh, so there is a derivative being taken. Sorry. Okay. Okay. But why is this nice? So the point is that now this is actually a degree d polynomial. So it's being applied to a vector. So I can, by a change of variables, I can map Lj of x to really, I can think of it as a, so when I'm taking a random x and y1 up to yd, so I can think of this as some vector x prime in f to the n. And I can think of alpha 1 y1, alpha 1 as just some y prime 1, alpha d Lj yd to be just y prime d. So what I mean by this is the following. So if I take the expected value of exponent of this guy, yd of is equal to really, so if I also normalize it by 2 to the d, this is going to be exactly under this transformation, the Gowers UD norm of E of sum of lambda I j prime of pi, where I is such that degree of lambda I prime j pi is equal to d. So now this now is where we actually pull out the uniformity, and we know that because this is a non-zero linear combination of my polynomials, not applied to any linear forms anymore, so this is bounded by epsilon. In particular, this is bounded by this 2 to the d, 2 to the d. So I promised some Cauchy-Schwarz inequalities, so that you can apply now to every step of the derivative. So we can actually, by a repeated application of Cauchy-Schwarz inequality, we know that this is an upper bound on what we wanted to show. Okay, which it's easy to verify that repeated application. So we don't actually, because so we lose it twice. So we gain it here, and we lose it here. So they kind of cancel out. Yeah. So we get exactly epsilon. So.
But this is written now.
Oh no, yeah. So this is okay. This was a. So when you apply the Cauchy-Schwarz, you gain 1 over 2 to the d. Yeah, great. Thank you. Okay, so this finishes the proof of the near orthogonality. Now I'll give a 10-minute proof sketch of the Gowers-Wolff conjecture. So it takes a little bit of work. So the idea is to use decomposition theorems and direct and inverse theorems for Gowers norms combined with our near orthogonality. So let me just briefly mention what the direct and inverse theorems say for Gowers norms are. Direct and, or maybe, inverse theorems. So there's many authors, as a result of works of many people. So the versions that we use are the Tal-Ziegler because we are over finite ones. So it says that, so the direct theorem says that if I have a function like this, then the UD norm is always an upper bound for the maximum correlation of f with E of p. For p, that's a degree d non-classical. And the inverse theorem, which is a much deeper theorem, so this follows by Gowers-Cauchy-Schwarz inequality. So this is a deep theorem that says that, in fact, an inverse to this also holds. D. So for every epsilon, there exists a delta such that UD being greater than epsilon implies that there exists a degree dp such that f correlates with it. And we will also use the decomposition theorems which as a shortcut, I will combine it with regularity lemmas for polynomials. And then I combine it for the fact that homogeneous polynomials span all polynomials. Homogeneous basis exists. And this will say that if I'm given, so this is a theorem, D. So let's say I'm given a collection of functions and I'm given an integer D, so we can write simultaneously, we can write our functions as gi plus hi such that the following things hold. So gi is a function of a collection of polynomials where p1 up to pc are uniform, homogeneous, and degree d. In particular, this actually obtained by averaging your function over the partitioning of the space that's provided by your polynomials. And the second important property is that you can have hi's are small. So I didn't quantify. There's a lot of epsilons and deltas. So the uniformity, you can have it as even as a function epsilon of the number of your polynomials. And so this will be smaller than a constant that we pick. Okay. So why is this useful for the Gowers-Wolff conjecture? So let's just recall what we have. So the setting is that are linearly independent. And we're given a set of functions, f1 up to fm. I will show that for every epsilon, there exists a delta such that if, in fact, the first function delta, then this average is less than or equal to epsilon. And this will imply the conjecture because, so f1, we don't use what it is, really. It could be any fi. So how do we use the decomposition theorem? So we really just plug in with sufficiently good uniformity and sufficiently good uniformity here for each of the fi's. So what this gives is that this is going to be approximately, and what d? So we choose d to be the Cauchy-Schwarz complexity. So as I mentioned, the Cauchy-Schwarz complexity can be infinity, but we can always reduce it to the case when it's not, because if one of the linear forms is another one times 2, let's say, you can combine them and think of the function as just the same function applied to.
So D here is exactly the D so that the tensor powers are linearly independent.
Oh, no, okay, sorry. So let S be the Cauchy-Schwarz complexity and apply decomposition theorem according to that. So now the point is that, so we will get each of fi's is gi plus hi, but hi has Gowers norm us plus 1 that is small. So now we apply the Green-Tao theorem. So we can drop those hi's from the expected value that I'm computing. So by Green-Tao theorem, since hi's us plus 1 norm is small, so we can approximate to any degree that we want with the same thing for the gi's. Right. And so it's sufficient to let's say take the uniformity to be like epsilon over 2m, so that this is by again a chain argument irrelevant, the terms that have hi. So it's sufficient to say that this is small, right? So how do we show that that is small? So we use this property of the gi's. So I know that gi is equal to something like this, where gamma I is a sum function. So now I actually use the classical, the Fourier analysis, a Fourier expansion of gamma I, and I can write this as a summation lambda c so these you have to be careful. So you have to pick each of them in the, let's say, zp to the k1 plus 1 dot dot dot. So the dual group of where they act. So now we plug this in here, expand out the whole thing. So what we get is really, so let's say this is star. Is equal to a summation of the product I going from 1 up to n of expected value of x e of p gamma, where p gamma is defined the same way as we defined it there. So yeah, so the point is that for each of them we have a linear combination. We're applying them to the linear forms, so we really get the form that we wanted. So now we actually argue term by term. So I'll just take 10 minutes to high level show how this. So we show that each term here will be bounded in the absolute value. Can be made as small as we want. And to do that, we break this into two cases. Case 1 is when the degree of, let's say, sum of lambda 1i pi of L1 of x. So this is p lambda 1 really, is less than or equal to d. 1 up to c. Okay. So when the degree is smaller than d, so how do we bound this? So the way we bound this is really by showing that, in fact, the Fourier coefficient, the first Fourier coefficient will be small. This is because f1 had a small ud plus 1 norm. And it doesn't correlate by the direct theorem for Gowers norms with any degree less than or equal to d polynomial. So, but you have to be also careful. So we're not working with f1 anymore. We're working with g1. However, correlation of g1 with any collection of polynomials that comes from the partitioning is equal to the correlation of f with it. So here we use, idea is use the fact that small can be made sufficiently small and direct theorem. So really the case 2 is the important one, where the degree of, so this is p lambda 1. However, in this case, we actually show that you can't have cancellation, so in the whole thing. So lemma is that in this case, p lambda is not 0. And if it's not 0, what can we do? We can go to our theorem. So if you don't have cancellation, you can, because the polynomials were uniform and homogeneous, this will imply that the expected value, so that this guy is really small, Oh, this is really small. This would imply that that's small. But how do we show that it's non-zero? So we assume that it's 0. So proof. Assume p lambda is 0. So now, so the way I like to look at it is just expand p lambda as like a matrix sort of summation. So p lambda is really p1 of L1 of x. So lambda 1 c pc. So we have, so this is sum of all of this will become p lambda. So the fact that p lambda 1 is at least of degree d plus 1 means that the first row has degree at least d plus 1. Right? So it means that there must be a term in the first row that has degree at least d plus 1. Now I just focus on that row. So let's say without loss of generality that that one is like this row. So I will just focus on this summation, now the column. And I have assumed that this is degree greater than or equal to d plus 1. But by the way we proved the near orthogonality theorem, we showed that if the whole thing cancels out, each column must cancel out individually. Because all the reductions we made, we focused on the same polynomial we made the reductions. Right? So in fact, we must have that this vanishes. But not only this vanishes, it vanishes for any homogeneous polynomial of the same degree and possibly lower depth. Right? And we know that at least there's one term that's not. So by what I just said, we know that sum of lambda 1 I p1 of Lm of x is 0. Okay. And without loss of generality, I can assume that there is at least a coefficient that's not divisible by p. So we can believe this, because otherwise you can just change p1 to be p times p1. So you can divide the coefficients by their GCD. So if I assume that, then by the near orthogonality theorem, in fact, sum of lambda 1 I q of Lm of x is 0 for all degree, for all homogeneous q of degree p. So now that we assumed this, so degree p1 and depth less than or equal to depth of p1. So now what do? We choose depth to be 0. So plug in just a monomial. So pick q to be just x1, x2 up to x degree of p. So what happens? All the terms here that have a coefficient that's divisible by p will be killed, because this is classical. So if you multiply it by p, so classicals are divided by p mod 1. So what you really get is a linear combination of this q, this monomial, applied to a bunch of your linear forms. But that vanishes. So it means that, in fact, you have contradicted this fact that these are linearly independent. So. So the tensor power comes from the coefficients of, yeah. So we are applying it to L1 of a bunch of vectors for x1, for x2, and so on. So when you multiply it, the coefficients are exactly. And the fact that it vanishes, it means that the same linear combination gives you the linear combination that they vanish. So this proves the Gowers-Wolff conjecture. Thanks. Oh yeah, so to prove that the true complexity is exactly this, we have to also show that the smaller d doesn't work. But that's not that complicated. So you just assume that there is a linear combination that's 0 now. So all you need to do is to construct a function. And you pick the function to be something like this. So you pick it as, you pick a very uniform degree d plus 1 polynomial, and you look at the following thing, e to the I times p of x, not e of I times p of x, I going from 1 up to p minus 1, and normalize it so that it will have the sufficient range. So now the point is that if you look at also plus, let's say, 1. So when you expand it out, you will exactly have one term that does have the cancellation. So you can pick this to be classical, in fact. And the point is that every time you don't have a cancellation, they have such a small bias that they don't matter. So in fact, this will be large. So the Gowers norm will be really small.